Alright folks, day 3, looking at finding limits, specifically finding limits at holes. So looking at some more techniques today as to how we can identify and remove a hole to find a limit. But before we do that, let's do a little review. Remember how to find limits graphically. So all these limits on the right here are looking at the x value of 2, but we're looking at it from the left, from the right, and then as a whole. So identify your x value of 2 right there. From the left, follow the graph up. Looks like we're going to that hole. From the right, follow the graph over. We are also going to that hole. So we are going to take the y value of the hole as our limit. So it's 1, 2, 3, 4. So the limit from the left is 4. The limit from the right is 4. And since the limit from the left and the limit from the right agree, the limit at as x approaches 2 is 4. Notice that is different than the value of the function at x equals 2. F of 2 is defined as 2, that little dot right there. Okay, let's look at the second set of limits. This time we're looking at the x value of 0. So from the left, and that's kind of messy, let's clean this up. So from the left and from the right, we are going to that y value of 1. So all those limits are 1. So let's look at this one now. Similar but slightly different. Still looking at the same two x values. From the left, as x approaches 2, I'm following that branch up to that point right there, which has a y value of 1. From the right, I'm following that upper branch over to that hole, which has a y value of 2. Since those two one-sided limits disagree with each other, the limit as x approaches 2 does not exist. It is undefined. And I'm fine with you writing DNE for that one. Does not exist. So let's look at 0 now. Well, 0 is going to be pretty straightforward from the left and from the right. They're both going to that y-intercept there, which has a value of -1. So all those limits are -1. So let's look at this third one now. Same two values, 0 and 2. So let's look at the x value of 2 first. Notice we have a vertical asymptote there. From the left, we're following that branch down to -infinity. From the right, we're following that branch up to +infinity. Since they are heading in different directions, they are not the same limit. We're going to say that this limit does not exist. Now 0 from the left, well, if you notice, we don't have any graph over here as part of our function, so we don't have a limit from the left. We do have a limit from the right. If we follow that branch up, we're heading to the y value of 0. But since we don't have that limit from the left, I'm going to say the limit there does not exist. And finally, one more, but whoa, 14 questions, and they're kind of hard to read, but I'll read them to you because I'm just that nice. First one is saying f of -5, and remember, that's just function notation. That's just saying evaluate this function when x is -5. Well, x is -5 right there, so go straight up to your graph. We hit that point right there, which has a y value of 6, even though it's hard to read. F of 2 is right there, our x value 2 is there. Notice the graph is up here, but we have a hole there. So notice they have defined that point right there, as the value of the function, which has a y value of 1. So the value of f of 2 is 1. Now, f of 4, let me clean some of this up. F of 4 is 1, 2, 3, 4 right there, straight down, which looks like we're at -1, 2, 3. So we're going to say f of 4 is -3. Our next limit says find the limit of f of x as x approaches -7. Well, -7 is right here where we have that hole. From the left and from the right, we're both heading to that hole, which has a y value of 2, so that limit exists and is 2. As x approaches -5, we're going up to the top of that shark fin that we've already found the value of. From the left and the right, it's going to the same point, which is 6. Notice that the value of the function is 6 at x equals -5, and the limit as x approaches -5 is also 6. That is our definition of continuity. So now let's look at the limit as x approaches 2. Well, again, there's x equals 2. As we approach it from the left, we're up there heading towards that hole. As we approach from the right, we're also heading towards that hole, which has a y value of 3. So the limit as x approaches 2 is 3. Now compare this with the last one we did. The limit as x approaches 2 is 3, and the value of our function f of 2 at x equals 2 is 1. These two values are different, those are different numbers, and so we have a discontinuity. We have a hole, and then our function has been redefined. Next limit we are finding is the limit of f of x as x approaches 4. So that's our x value of 4 right there. From the left, we're up on that branch going towards that hole, which has a y value of 2. From the right, we're down on this branch going towards that point, which has a y value of -3. Since those two values are different, we're going to say that limit does not exist. Because again, for a limit to exist, the left-handed and right-handed limits have to agree with each other. 8 says the limit as x approaches 0. Well, notice at x equals 0, we have a vertical asymptote. To the left, it's shooting off towards -infinity. To the right, it's shooting off towards +infinity. Different values, so that limit also does not exist. But we can answer this question. The left-handed limit, limit as x approaches 0 from the left, we've already identified as -infinity. From the right, +infinity, so again verifying that the limit as x approaches 0 does not exist. Whew, almost there. Limit as x approaches 4 from the right, we already said was -3. From the left, we said was 2. So I don't know why they decided to put these in this order. It doesn't really make sense. But again, reinforcing the idea that the limit as x approaches 4 doesn't exist. Now the last two, we're talking about infinite limits. Limit as x approaches -infinity. Well, look over here. It looks like we have our graph leveling out to the y value of 0. So I'm going to say the limit as x approaches -infinity is 0. And the limit as x approaches +infinity, again, we're leveling out to 0. So that limit is also 0. So now we're going to jump into a new algebraic technique to find a limit. And to get us there, we are going to remember what it means to rationalize something. So last year, you probably remember this value, 1 over the square root of 2, and we want to rationalize it. And to do that, remember, we can't change the value of the function. All we can do is multiply by 1, but we can be clever about how we do it. So I'm going to multiply by the square root of 2 over the square root of 2. Remember how to multiply fractions. You just multiply across the numerator and multiply across the denominator. So in the numerator, I get 1 times the square root of 2, which is the square root of 2. And in the denominator, I get the square root of 2 times the square root of 2, which is 2. So I have rationalized my denominator. Let's look at a slightly trickier one, square root of 2 minus 3. Here I'm going to use the idea of conjugates like we did last unit with imaginary numbers, complex numbers. So I'm going to multiply by the square root of 2 plus 3 over the square root of 2 plus 3. Notice square root of 2 is the same, the 3 is the same, I just changed the minus to a plus. When you multiply these out, remember when you multiply conjugates, a plus b times a minus b, we have a difference of squares. It becomes a squared minus b squared. And think about it, that's how we factor, if you go that way, that's how we factor a difference of squares, like x squared minus 1 factors as x plus 1 times x minus 1. We're using the same idea here so that when we multiply the denominators together, we're going to get the square root of 2 times the square root of 2. Our a squared term becomes simply 2. And we get our b squared term is 3 squared, which is 9, and we're subtracting it. So we got rid of the square root down there. And in the numerator, just multiplying by 1, so we get square root of 2 plus 3. And I could, of course, simplify this a little more. Square root of 2 plus 3 over negative 7, and you could keep doing some more things, but that's good for us for now. So now I'm going to ask you to do something that seems counterproductive. I'm going to ask you to rationalize the numerator. But I have a reason for this. It's not going to work any differently. I'm going to multiply it by the square root of 3 minus 5 over the square root of 3 minus 5. Again, just using that idea of the conjugate. So in the numerator, I'm going to get 3 minus 5 squared is 25 over 3 times the square root of 3 minus 5. And I'm just going to simplify that to negative 22 over 3 times the square root of 3 minus 5. I'm not even going to bother to distribute that in. I just wanted to practice this. And you, again, will see why in a moment. Now, it may seem kind of productive because we normally are trying to get the square roots out of the denominator, and this time we move the square root to the denominator. But have patience and you will see. So let's do this one now. It has an x in it, but that's okay. It's going to work the same exact way. We're going to multiply by the conjugate of the numerator, so square root of x plus 1, all in square roots, plus 1 over the same thing, x plus 1 plus 1, and let's see what happens. Notice in the numerator, again, we're just going to get what's underneath the square root, the argument there, x plus 1, and then we're going to subtract our b squared term, so 1 squared is 1 over x, and again, I'm not going to distribute in x plus 1 like that, and look at what happens in my numerator. 1 minus 1 simplifies to x over x times the square root of x plus 1 plus 1. Well, look what happens. We have an x in the numerator and an x in the denominator, so we can cancel those out. And this is going to simplify to 1 over the square root of x plus 1 plus 1. Why is that useful? Well, I think you might realize why it's useful because we essentially just took out a hole. We identified a hole and we removed it. That is our technique that we're looking at today, rationalizing numerators. So if we do this problem, which is exactly the same as the last one, notice that is the same function we're looking at. So when we rationalize it, we're going to get the limit as x approaches 0 of what we just found, the 1 over the square root of x plus 1 plus 1. Notice why we like this. Our limit is going to 0, so we cannot just directly substitute 0 in because that denominator would equal 0. But now that we've taken that whole out, 0 no longer makes our denominator equal to 0. So we can directly substitute in to get 1 over the square root of 0 plus 1, which is going to simplify to 1 over the square root of 1, which is just 1, plus 1. So we get 1 half. So let's try that approach here with this limit problem. I'm going to do a little side work here rather than rewriting all those limits. So let's multiply by the conjugate of the numerator. So the square root of x plus 4 plus 2 over the square root of x plus 4 plus 2. Again, when we multiply that conjugate by its conjugate, the numerator by that conjugate, we are going to get what's underneath the square root sign, so x plus 4, then 2 times 2 is going to give us another 4, and we're subtracting it. So look what's already happening. And then denominator, I'm going to get my square root of x plus 4 plus 2. And again, we're happy because 4 minus 4 is 0, and x over x simplifies. So we get 1 over the square root of x plus 4 plus 2. So I'm going to rewrite my limit problem, and now I can directly substitute in to get 1 over, notice since x is going to 0, that term is just going to be 0, so I'm going to get the square root of 4 plus 2. Well, the square root of 4 is 2, so I'm going to get 1 over 4. The limit of that function is 1/4. So, same idea here. This time we've got kind of a crazy number up there in the numerator, 2 root 3 but our technique is going to be absolutely the same. We're going to multiply by that conjugate. So when we do that, again, we're going to get whatever's underneath the square root, which is x plus 12. And now we need to think about what 2 root 3 squared is. And notice I'm squaring the whole thing, even the 2. Well, that's the same as 2 root 3 times 2 root 3. So think about, let's rearrange this. Let's go 2 times 2 times square root 3 times square root 3. Well, 2 times 2 is 4. Square root 3 times square root 3 is 3. And then simplifying further, 4 times 3 is 12. So do not mistakenly just square the square root of 3 part and get 6. That will be incorrect. And remember, we are subtracting that square, so we're going to get minus 12 up there. Denominator is going to become x times that conjugate, square root of x plus 12 plus 2 root 3. And so again, my 12 and my minus 12 are going to cancel out. My x and my x are going to cancel out, so my numerator becomes just 1. And now I can rewrite this limit problem. So at this stage of the game, now I can just directly substitute in, and I will get 1 over the square root of 12 plus 2 root 3. And that is definitely your limit, but that's a really ugly number. You would never see that as an answer for a multiple choice AP question. So we need to simplify this, and we need to rationalize the denominator. So remember that the square root of 12 is the same as the square root of 4 times 3, which is the same as the square root of 4 times the square root of 3, which is the same as 2 root 3. So hopefully you can follow that there and apply it later. But I'm going to rewrite this as 1 over 2 root 3 plus 2 root 3, which is the same as 1 over 4 root 3. And now I want to rationalize that, so I'm going to multiply by root 3 over root 3. And whoa, look at all that work. In the numerator, I'm going to get the square root of 3, and in the denominator, I'm going to get the square root of 3 times the square root of 3, which is 3, times 4, which is 12, and that will be my final answer for this limit problem. So let's look at 2 more. These are all working the same way, so plenty of practice by now. But this time we're going not to 0, but to 5. And again, we can't directly substitute in because 5 as an x value makes that denominator equal to 0. So let's do our side work again. So when we multiply those conjugates together, we're going to get x plus 4 from that square root minus our b squared term is going to be 9. And that's all over x minus 5. And I messed this up right here. I should have written the square root of x plus 4 plus 3. So let me fix that. Now this time, notice what happens. We don't just end up with an x in the numerator, because 4 minus 9 is negative 5. But we do end up with an x minus 5. And notice why that's good, because we have an x minus 5 in the denominator. So let's finish this off, throw that thing there. It's too big though, let's make it smaller so it'll fit. And now, same thing in the numerator and the denominator. So we can get rid of them, replace that with a 1. And so we get 1 over the square root of x plus 4 plus 3. So let's write our limit as x approaches 5 of 1 over the square root of x plus 4 plus 3. Now we can directly substitute in, so we get 1 over the square root of 9 plus 3, which is going to give us 1/6. So last problem we're going to look at, limit as x approaches 2 of the square root of x plus 14 minus 4 over 2 minus x. So we're going to approach this the same exact way and multiply by the conjugate of the numerator, and we're going to get x plus 14 minus 16, because 4 squared is 16, over 2 minus x times the square root of x plus 14 plus 4. Simplify this a little bit farther. Numerator becomes x minus 2. Denominator is still the same. And you may be thinking, oh no, my numerator says x minus 2 and my denominator says 2 minus x. Well, think about this. Let's play with that numerator. Notice that those two expressions, x minus 2 and 2 minus x, are the same, except that on one of them the signs are changed. Well, if I take x minus 2 and I factor out a negative 1, that's going to be the same as 2 minus x. And convince yourself, throw that negative 1 back in, your 2 becomes a negative 2, your x becomes a positive x, and it does indeed work. So this is again going to cancel out, except this time we're going to be left with a negative 1 up there. So this limit is going to become negative 1. Oop, I'm sorry, I should still write that limit. So now that I've written my limit, I can now substitute in to get negative 1 over the square root of x plus 14, so 2 plus 14, so 16 plus 4, and that will simplify to negative 1/8. And that is all we're going to do in this lesson. So quick closure, explain how the first technique, rationalizing the denominator, that should say actually rationalizing the numerator. How is this similar to what we did with complex conjugates? Well, last unit we used complex conjugates, so if we had a plus bi, we multiplied that by a minus bi to again get a squared minus our second term squared, which was b squared I squared. In that case, we ended up with a squared plus b squared, because I squared is negative 1. We're doing the same thing here with the square roots. This time we're just simply using a plus b times a minus b to again get that difference of squares, which is a squared minus b squared.